इधर नहीं है प्लग नीचे नहीं है।
उसको इन्वर्ट कर दो ना। No, sir. Sir, are we audible, sir?
Yeah, very much.
Yes, sir. We are live on YouTube now with the Google Meet. So
Okay.
I'll formally ask Ashish to welcome us all.
आज के मुख्य वक्ता डॉक्टर आलोक श्रीवास्तव, आउटस्टैंडिंग साइंटिस्ट एंड उपनिदेशक मैकेनिकल सिस्टम एरिया UR राव सैटेलाइट सेंटर URSC बेंगलोर। श्री आनंद पाठक SSME अध्यक्ष, श्री सुशील टेक्निकल डायरेक्टर अल्टेर, श्री उल्केश देसाई उपाध्यक्ष SSME, इसरो के महानुभावों, सभी कार्यकारी समिति के सदस्यगण, ऐसे सदस्यगण, अल्टेर के अधिकारीगण, विद्यार्थियों और ऑनलाइन माध्यम से जुड़े सभी श्रोताओं को SSME के सदस्य सचिव आशीष सोनी का प्यार भरा नमस्कार। सर्वप्रथम आज के मुख्य स्वागत है आपका श्रीमान, स्वागत है आपका श्रीमान। वेलकम डॉक्टर आलोक सर।
धन्यवाद।
आप सभी श्रोतागण का स्वागत करते हुए मैं यूं कहना चाहूंगा कि दिल को सुकून मिलता है मुस्कुराने से, दिल को सुकून मिलता है मुस्कुराने से, वेबिनार में रौनक आ जाती है आपके आने से। आप सभी श्रोतागण का भी हार्दिक स्वागत है। मैं पुनः आप सभी का स्वागत करते हुए आगे बढ़ता हूं। आज है दिनांक 15 सितंबर और आज का दिन हम सब के लिए सविशेष है। आज का दिन सविशेष इसलिए है क्योंकि आज अभियंता दिवस है। आप सभी को अभियंता दिवस की हार्दिक शुभकामनाएं। विशिंग ऑल ऑफ यू अ हैप्पी इंजीनियर्स डे। And about Engineers Day, I would like to brief that Engineers Day is a name suggests is a day dedicated to all engineers. It is celebrated annually on 15 September to mark the birth anniversary of Indian civil engineer Bharat Ratna Shri Mokshagundam Vishweshwaraya, who born on 15 September 1860 in the village of Karnataka. He completed his engineering degree from College of Engineering Pune and went on to the work on the several projects which contributed significantly to Indian society. He was conferred with several awards and honors like Bharat Ratna, Knight Commander of the Order of the Indian Empire KCIE, and many more. This day highlights the importance of engineers in modern society. In ISRO, we are having designation of scientist and engineer. And for this both designation, I must say that scientist dreams and engineers fulfill those dreams. So science is about knowing, but engineering is about doing. Science is discovering the essential truths about what exists in the universe, and engineering is about creating things that never existed. और आज इस विशेष दिन पर ऐसे ही एक सविशेष वैज्ञानिक अभियंता आलोक सर हम सब के बीच में मौजूद है और उनके परिचय के लिए मैं आमंत्रित करता हूं श्री उल्केश देसाई को। धन्यवाद।
धन्यवाद आशीष. At the outset, I would like to thank Dr. Alok sir for kindly accepting our invitation. I know, sir, you are very busy with all your responsibilities, but still you could devote time for SSME and this webinar. Thank you very much, sir. I'll just briefly, for the benefit of the audience, talk about Dr. Alok Srivastav. Dr. Alok Srivastav is an outstanding scientist and he is the Deputy Director of Mechanical Systems Area. He was the former Group Director of Thermal Systems Group at URSC. He was also the Project Director of INSAT 3D, INSAT 3DS, GISAT-1 and GISAT-2 satellites. He is a gold medalist at graduation level from College of Engineering, Bilaspur, and he's completed his PhD from IIT Bombay. He joined ISRO in 1987, and since then he was involved in the thermal design, thermal management of various multi-purpose spacecrafts like INSAT 2A, Chandrayaan 1, Chandrayaan 2, Mars Orbiter mission, as in various capacities as project manager, deputy project director, and even as project director. He has handled many projects outside URSC also as a special expert for missions of LRD, DRDO. He is on the reviewing body of many international journals, specifically International Journal of Heat and Mass Transfer, International Journal of Engineering Practical Research. Two of his engineers have completed PhD under his able guidance, and many are pursuing PhD under his guidance. He has put immense efforts on indigenizations and patents of all the ISRO technologies which are developed for ISRO satellites. He has published more than 32 papers in national and international journals and has more than 250 internal reports of ISRO. Notably, Sir has received ISRO Team Excellence Award for Chandrayaan-1 spacecraft, Astronomical Society of India Award for year 2007, and ISRO Award for year 2016. He has delivered more than 215 technical lectures in English and Hindi, and many of us in ISRO and in the YouTube and in the DD National have heard his voice during all the ISRO's launches. He has covered more than 30 launches, including the Mars Orbiter mission and Chandrayaan-2 from ISTRAC. I am very glad to say that Sir has accepted our invitation and he will be delivering the lecture today. Thank you very much, sir. And I invite Alok sir to deliver his lecture.
Thank you, Ulkesh. And my dear friends, Anand, Ashish, Vivek, and all the audience today available through video mode, through internet mode, and YouTube. I'm really honored to give a talk on this subject. But strictly speaking, many things are going on in my mind right now. I'm just thinking, start from where and talk what all, because so many things have been talked so far, right from the spacecraft and also about the thermal control systems, and presently being part in the mechanical systems area. structure and mechanism also I'm learning. I'm learning the satellite technology from electronics perspective, power perspective, and communication perspective, along with the mission and managements. So I'm really I can say that I'm just joining the spacecraft building. Am I audible and my slides are visible?
Yes, sir. You are
Yes, sir.
audible and your slides are also visible,
Sir, one request to all the viewers that viewers can type their questions in that YouTube chat box. Mr. Amit Agarwal is moderating this session and he will ask all the questions to sir on your behalf. So viewers are requested to type their questions in YouTube chat box. Thank you, sir. Please go ahead, sir.
Yeah, thank you. Once again, I personally feel very, very sorry to Ulkesh because 2 times I couldn't take his call in time. The reason was not that I'm busy, but its reason is some meeting will be going on, so it was difficult to come out and take the call. So thanks for giving me opportunity to talk to my audience today, which are engineers mostly, not only within ISRO, beyond ISRO, and students in the academic institutes. So it's from this aspect. So I am really feeling very thankful to this society for giving me an opportunity. I'll try to start and finish within another 50 minutes to 1 hour and try to give you a glimpse of. I cannot assure you that you'll become expert in thermal, but I would like to give you a glimpse of what's going on in ISRO in thermal and what are the upcoming technologies which are really essential. The journey commenced in 1963. That was the year when I was born, so I never thought when I was studying that once upon time I'll be really delivering a talk in ISRO, which was really a dream of our father of space science in India, Vikram Sarabhai sir from Gujarat. And he says that our whole effort should be that we should be second to none in this technology, and our technology development, the progress should be very close to man and the society, the societal application we must try to address, and also the progressive attitude should be such that the lost man in the society also should get benefit out of it. Actually speaking, the space, what we talk about right from leaving the Earth's atmosphere, it is very harsh. The temperature is close to 4 Kelvin and the pressure is close to 10 to power minus 12 torr. It means absolute vacuum. That clearly indicates that out of the three modes of heat transfer, conduction, convection, and radiation, convection becoming absent, which is predominantly a very effective mode of heat transfer. But the God, once he takes, gives you much more. He has given you radiation, heat transfer, and temperature is absolute zero. So it's an excellent sink which is available around the craft which we send from here called as a spacecraft, and which when it reaches there and serves the society, serves the purpose for which is intended to build. The satellite, when it leaves the Earth's atmosphere, it has to pass through several belts, which is nothing but known as radiation belts like Van Allen, Kuiper belts, and so on. They are the torus of the highly energized particle. So we must have to safeguard our electronic package and the satellite from getting affected and destroyed by this kind of belts. Many of the spacefaring nations, they have lost their satellites due to that. With all such odd condition, also still human would like to go, because from deep space, the global look of the Earth is much, much better compared to at an altitude from where even we can say that our aeroplanes will be there. So from that aspect, it is very essential that we will be in a position to look at it. So that is the advantage we would like to encash. This is what I was talking about, that about Earth's atmosphere, there is a torus of highly energized particle through which the satellite or any such body which would like to go for interplanetary mission, which has to pass through. My dear friends, many of the times you might have seen in the net, in the Google, that the mission which NASA has sent, Apollo missions, They are all hoax. In fact, the reason behind that is people say that those days the technology was not even available to overcome this kind of radiation shielding. So this is one of the typical belt which is all around. Of course, ISRO has done a good job in building the satellite right from after in 4 satellites in INSAT class, which Ford Aerospace USA has built is for us INSAT 1A, 1B, 1C, 1D out of the 2 satellite successfully worked and but 2 failed. After that, INSAT 2A was the satellite which ISRO has built and then never looked back and started from C band and S band to coming up to KU band and Ka band. It has done a very good job for various kinds of application like speech circuit, trunk routes, TV broadcasting, business communication, and so on. Similarly, for the remote sensing application, if you just look at it today, we cannot even think of any part of the society which we don't touch, be it agriculture, be it forest, water resource, geology, ocean, or environment. We touch almost all the parts of the society by our application, by our the societal need. For example, typically when we would like to imagine the earth, whether it's for the hurricane or any kind of weather forecasting, typically the picture which you are seeing on the top, it is nothing but imaging, while the picture which is there nothing but at the down, which is nothing but the vertical imaging known as the sounding of the atmosphere. So basically it is imaging and sounding combination which has been made it very apparently for the purpose of using for weather forecasting.
Alok sir,
Initial, yeah.
sorry sir. Can you put your presentation in presentation mode, sir? Thank you, sir.
Already it is in presentation. I would like to redo that again.
Actually, slides are not changing, sir.
Slides are not changing. Just a moment. Let me try once again.
Right.
Oh. Oh. Yeah, I think there is some net issue. It's not allowing me. I'll just try once again. Whether it is visible now?
Yes, sir. Now it is visible there, sir. Right, sir. Perfect, sir.
Okay. So we started the weather forecasting services by imaging. This is typically a payload which is developed by Space Application Center, Ahmedabad. And this is typically because I am concentrating my presentation today on thermal control system. So these detectors which will sense the energy which is coming to the spacecraft only if the temperature of the detectors are maintained at a very low temperature. So on the left side figure, whatever the two which I am putting the cursor there, they are known as the passive radiative coolers. And similarly left side there is a filter wheel cooler. So there are 3 types of coolers which will maintain the temperature around 90 Kelvin. So this is a very demanding requirement. So the Earth's energy goes and reflects back onto the mirror, and the mirror finally goes to primary mirror, from where the energy goes to secondary and finally gets split into various IR channels for the different purposes. So this is a exploded view which I'm not concentrating, but I would like to concentrate on this figure right now. The red patch, whatever you are seeing, that is the low level where we get the temperature of typically, like for example, outside whatever you are seeing is 150 Kelvin, and inside whatever that cursor where I'm keeping is around 90 Kelvin. Similarly, there is another cooler here. So this is the typical exploded view, which is a 3-stage cryo cooler developed by Thermal Systems Group URSC, which was earlier known as ISRO Satellite Center, which was led by my seniors and my thermal engineers who have put their enormous effort contributing and evolving this coolers in the form of what we get right now is appearing something like this with the gold coating. Basically, gold coating is nothing but making the surface very, very low emissive. Emissivity is one of the characteristic of the surface because of which the radiation interaction becomes very, very less or almost negligibly small. And that's how we try to minimize or try to improve the temperatures. So this, and then we have the left bottommost picture, whatever seeing, that is small rectangle there, that is what is the patch where we get the temperature around 90 Kelvin or so, and this is the finished product which comes. Similarly, there is a rotating body, and rotating body temperature needs to be maintained at around 150 Kelvin, and the condition which was put forward, the constant which was put forward, the bottom one, there is a motor which is running at with a dissipation and maintaining a temperature around 30 degrees Celsius, and the top side we need a temperature around 150 Kelvin. So you can understand that what is the level of temperature difference has to be maintained, and then you can say that, so we have designed a shaft which is made up of composite and a low emissivity material like titanium with end fittings, and this is done by our along with our composite from VSSC. We have evolved the total system along with the IISU, and we have got this kind of composite cylinder which has made it is possible to achieve this temperature, and this is that filter wheel cooler whose temperature nicely we could manage approximately 150 Kelvin or so. So you can just see that the two satellites which is there in space, that is INSAT 3D and INSAT 3DR. So basically, if any hurricane or any such kind of storm are getting developed in so INSAT 3D and INSAT 3DR, every 15 minutes they will try to have the data which will be flowing. So though one satellite takes 30 minutes, but two satellites together, it will take roughly 15 minutes. So every 15 minutes, not only whether this cyclone movement horizontally, but vertically also we can monitor, and in this way accurate prediction can be made. And here thermal plays a significant role, and this is the reason why I'm just giving introduction where all thermal becomes very crucial and how. After having a good knowledge about the communication and then remote sensing, the quest for the knowledge continued for X-ray astronomy and once in a blue moon for the events like gamma ray burst and so on. So many of the scientific satellites also were planned from the ISRO side, right from Aryabhatta satellite, which was in 1975 onwards. So we have put astronomy and astrophysics study for the sun and moon and Mars. We have done so many satellites, typically 3-4 satellites, I'll try to name it. In 2008, we have a Chandrayaan-1. This is the only satellites globally which has got 11 instruments on board with so many spacefaring nations, so many space agency came together like JPL, NASA, Brown University, Rutherford Appleton Laboratory, Max Planck Institute, IRF, Sweden, European Space Agency, JAXA, Japan, and so on. And we build the satellite for the purpose of observing the moon for the different reasons. So per se, there are more than 200 reasons which have been documented for exploring the moon, which is nearest celestial body, and we have the least information globally about this body. And another thing which is very, very essential is when for the first time this responsibility was given to me for designing this Chandrayaan-1. I was a little bit surprised that what is so difficult in designing. And later on, when I continuously did the literature survey, I found that many satellites went to that field because of thermal. The reason is, if you can just look at it, the left portion, which is a red dot, the temperature is approximately 123 degrees Celsius, which is known as subsolar point. And the outer side, that rear side of the moon, which is the right side figure, it's almost minus 170. So you can say that if the orbit is approximately 1000 kilometer altitude, it will take approximately 2 hours to orbit with the temperature variation from 123 to minus 170. So any electronic body will develop a thermal stress in case it needs to face every 2 hours this kind of excursion. So it was very essential. And the most important, at 123 degrees Celsius, using Stephen Boltzmann law, if you try to estimate what will be the approximate flux which will be coming, it will be approximately 1290 watts per square meter. And the sun energy which comes at this altitude on the moon's orbit is also equivalent to around 1353 watts per square meter Celsius watts per square meter. So you can say that we need to design a satellite with the 2 sun configuration, and that was the challenge. Similarly, the Mars orbiter mission, which we wanted to make it to fly in 2014, but between 2014 and 2008 we wanted to have a follow-up mission of Chandrayaan-1 in the form of lander and rover. And that time it was Russian who were supposed to give us lander and rover, but later on, due to some reasons, it was not made available, and we have to develop, ISRO has to develop its own lander and rover. So what happened is, in between that, we have taken Mars orbiter mission, and then this was the Chandrayaan-2 mission across the globe. Now entire world is known that it was our maiden effort, which became a great success, Mars orbiter mission. But then we came a Chandrayaan-2. By the time we had a orbiter as well as a lander, as you are seeing in the picture. So orbiter was supposed to form the exactly same configuration like our Chandrayaan-1, which will be orbiting around the moon surface at an altitude approximately 100 kilometer circular, but instead of circular, they made it little elliptical. And similarly, the lander, which was having lander plus rover configuration, was supposed to separate from the orbiter at certain altitude and land on the surface and rover. We could achieve certain objective, but yes, of course, we all know that we could not land appropriately from certain altitude due to technical slag or glitch. But ultimately, what I am going to talk about today is the thermal controls, thermal technologies, which are very, very essential for the satellite building in the space science. So they all becomes very, very important depending upon the satellite is made for what. For the low Earth orbit, for geostationary orbit, for geosynchronous orbit, or for what application, like communication purpose, remote sensing purpose, navigation, or even for the International Space Station or for the human mission like Gaganyaan and so on. So depending upon the orbit, depending upon the altitude, depending upon the application, the thermal control which will be applying will be different and very, very challenging. So let's talk about the thermal control system. The spacecraft per se we can divide into 2 parts, the bus and the payload. The bus is nothing but which is meant to serve the purpose of the payload which is going to support. So like any other common sense in the layman's language, if I talk, we do a lot of journey in the railway or in the buses. So bus is nothing but like our chassis will be there, body will be there, steering will be there, and windscreen will be there. So there are so many part of the bus. So similarly here, the bus is nothing but a structure, mechanism, thermal, electrical power, telemetry, telecommand, attitude, and propulsion system, and so on. But the basic purpose of the satellite for which it is built is nothing but the payload. For example, when we do the journey, we are supposed to sit in the bus. So for bus, we become the payload. See here, like communication, like transponder, if our objective is do the communication satellite, communication science, then communication payloads like transponder becomes the payload. Suppose we want a weather forecasting, so meteorology application, so they become the payload. Like we had a very high resolution radiometer in the beginning, and later on imager and sounder like a GOES mission from the across the globe. So similarly, Earth resources. Now these are the uses of the satellite. They become those scientific instrument becomes the payload. So typically we divide the whole satellite into these components. Now, why temperature control is needed? Electronic components can work only for a limited temperature range, and every 10-degree rise in temperature roughly reduces the life to almost half, you can say. Batteries, they may reach thermal runaway condition at a high temperature and reaction rate may slow down on electrolyte may freeze at a lower temperature. So battery life increases at a lower operating temperatures. Requirement of low thermal distortion for earth observation, be it camera or something like optical or telescopes. Propellant may freeze at a low temperature, and high temperature may cause excessive degassing or damage to elastomers. So it's very essential to build them. Similarly, IR detectors. Just now I have given an example of INSET 3D and INSET 3DR. So those are the detectors which they function satisfactory at very low temperature, like I gave an example of 90 Kelvin. Otherwise, they will cease to function. So these are typical example why we need to maintain, why we demand the temperature there. But important phases also we need to maintain the temperature. For example, when we want to have the assembly of the satellite in the clean room, when we want to assemble the components on the panels in the decks, then we need to maintain the cleanliness, relative humidity, as well as temperature of these chambers. So thermal control also become part of that. So similarly, when we want to keep the test the satellite in the chamber, we create the same environment, similar environment which is there in the deep space, similar order, but not exactly same as the deep space. So where we try to maintain the temperature even that phase. Similarly, on the launch pad. So when we keep the satellite on the top of the rocket, which you are seeing here, which I am using as the cursor, the top nose cone. Here we keep the satellite, which is known as this payload fairing for the rocket, or heat shield. So this is the last stage of the vehicle. Typically, like PSLV, when you talk, it is the fourth stage, or GSLV, when we talk, it is 3 stage, like Ariane, it is 3 stage, such kind of vehicles. So on the last stage, we keep the satellite, and then we keep the other half completed, so that it becomes like a cylindrical conical surface here. So we try to maintain the temperature even during this period. If by chance, if the launch gets delayed, or if it rains, we need to protect it. So if the sun falls directly, or in the cold region, like if the rocket is in Russia, so in the cold we want to protect the satellite, so we need to control the temperature. Similarly, at the launch phase, so you have to take care about the satellite during the launch also. In different phases, when the stages gets separated up after the boosters, then the payload fairing gets opened up, the satellite gets exposed to the deeper environment after the second and third stage gets exposed. And when that happens, the satellite gets exposed to environment, and that time also temperature needs to be maintained, as you are observing here. Similarly, in case intermediate orbit, before the satellite reaches its final orbit, when we inject the satellite, we'll be injecting at the elliptical orbit, but that is called as a transfer orbit. So then we will be doing orbit raising, like our general remote sensing or communication satellite, before reaching it through drift orbit into final orbit, or Chandrayaan 1, Chandrayaan 2, or Mars orbiter mission, or upcoming Aditya mission, we would like to have we call as a low transfer trajectory. So we will be injecting the satellite into low elliptical orbit, and then slowly we will be trying to raise the orbit, and then there will be a point from where we transfer the trajectory from the Earth's atmosphere to Moon's orbit, and then after that we try to capture it in the Moon's orbit and try to reduce the orbit to make it a circular orbit. So this is a very highly calculated thing, and during entire phase, thermal job is to maintain the temperature there. For all the electronic element, all the battery, all the propulsion element within the timeline. Moreover, till the end of the life, typically for remote sensing satellite, 5 years to 7 years life. For the communication satellite, it can be at 10 years, 12 years to 15 years life. We need to maintain the temperature of all the equipment 365 days, 24/7, 365 days. And that is usually done using our appropriate thermal control systems, which can be passive or active, which I'll be talking afterwards. So there is a degradation of the optical properties. That property degrades. It means that alpha, the solar absorptivity, which is the optical property of the external surfaces, goes up. When it goes up, it starts absorbing more and more heat load from surrounding, and the temperature of body goes up. So this is also very important phenomena. The contradiction is different. Contradiction is here that all these things, we need to launch a lighter satellite. Lighter means we need a composite or we need a honeycomb structure. Honeycomb structure is an anisotropic material, as all the engineers are fully maybe familiar with. It is a high stiffness, high strength, high thermal stability material, but the problem is it is not very thermal friendly. It has got very low thermal conductivity, and that too different in different direction. So we need to really use this opportunity to do that. And this is typically like I was talking about a honeycomb structure. This is a honeycomb beehive, like a shell will be there with aluminum foils using glues with both side face sheet thickness of typically like 0.2, 0.25 or 0.5 mm depending upon the application. And this how we make the honeycomb on which the packages will be kept. They are very extremely low weight, but very good strength, but very poor thermal conductivity. So this is something which we need to worry about. And along with that, with upcoming days, those were the days gone when engineers were using whatever material is given to them. Nowadays, younger engineers, they are demanding what property they need in the given material. So materials are go on getting evolved by various kinds of, typically like carbon fiber reinforced plastic, CFRP. This kind of material which has got a lot of benefits. In fact, we started with a very low thermal conductivity in the different direction. So this is also an isotropic material. But what happens is it has got very good strength. It has got all the advantage, very lightweight, but very, once again, not very thermal friendly. So the reason its utilization became less unless and until we started getting high conductivity fibers also. So this was all about having contradictory all around the thermal design engineers, the constants around thermal design engineers. So design drivers, what design drivers are there for thermal control systems? So basically spacecraft and orbit configuration, you should know operating environment, you should know power dissipation and its distribution in satellite, you should know temperature requirement of various subsystems should be known to you. And once all this information is known to you, then lot of input a thermal design thermal radiator. For example, in this picture, whatever you are seeing it, there is a package which is having heat dissipation, which is mounted a honeycomb deck, which is I have already explained to you, and outside surface which will be seeing into deep space. So then outside property, if you can appropriately select that alpha, solar absorptivity, and emissivity, what is nothing but a property of the surface, then immediately you will be able to achieve the balance in such a way that appropriate temperature can be obtained. So basically it is a balance of heat in and heat out. So the balance enthalpy which will be responsible for the temperature rise of the body, there is no big science in that. So effect, and typically there are 5 properties which are responsible for the thermal management, that is a K, rho, Cp, alpha and epsilon. K is thermal conductivity, rho is density, Cp is the specific heat, and alpha epsilon are the 2 optical property which you people have studied in the graduation level or school level. So these are the total definition which